Now that we've reviewed linear systems of equations, let's look at nonlinear systems of equations. In nonlinear systems of equations, at least one of the equations is not a line. So in this set of pictures right here, we're combining a parabola with a line. And we have more than just the three possibilities we saw last time. Well, we have three, but they're different. With lines, they either cross once, they're the same line, or they never cross. With a parabola and a line, they either never cross, which is what you see here, an inconsistent system, or they cross once, just barely skimming each other at one point, or the line cuts through the heart of the parabola, and there are two solutions. So we have different options for a consistent system. And there's no such thing as dependent, because if you have a parabola and a line, they obviously won't be the same. Now, there are other kinds of curves we can take as well. This is a circle with a line. And again, they don't have to touch or cross at all, so there'd be no solution in inconsistent system. Or there could be one solution where it barely touches, is what we call tangent to the curve. Or it can cut through the circle across both sides, creating a chord, and then there are two solutions. Now we can do the same thing, of course, if we have an ellipse. Oops, I guess I should choose a different color for the ellipse. If I have an ellipse, I could have something over here, no solution, or I could make it barely touch at one point, one solution, or I could make it cut through, and then there are two solutions. And we'll see that this latter two types, the ellipse with the line or the ellipse with the, or the circle with the line, these can be solved in various ways. We can do substitution. It's not usually possible to do addition elimination. Now, when we're looking at the line and the parabola, we generally, again, have to use substitution. We generally don't use addition elimination. So would we ever use addition elimination? We can use addition elimination, but it's less common. It's much less common. So what would be a situation where we'd use addition elimination? Well, we could have an ellipse intersecting with a circle. In that case, we could use addition elimination to solve the system. Now, again, they could either not cross, they can cross twice, they can actually cross 4 times, or they can cross 1 time. So how could it cross 4 times? You can just do something like that, and there are 4 points of intersection. So there are more possibilities with those conic sections. Let's take a look now at how to solve a system of nonlinear equations containing a line and a parabola. If it's a line and a parabola, you're going to use the substitution method. You're going to solve the linear equation for one of the variables, and then you're going to substitute it into the parabola equation. Then you'll solve for the remaining variable, check your solutions in both equations to make sure you haven't made a mistake. If you are solving a system with a line and a circle, then you're again going to solve the linear equation for one of the variables, x or y, whichever one has a 1 coefficient, if possible. And then you're going to substitute that into the equation for the circle, solve for the remaining variable, and check your solutions. So here are some different possibilities that we have with the circle and the ellipse. So you can see there are different ways that they can interact, and there are all different kinds of solutions. We can even get 3 solutions, as you see here in the 4th picture, right? A lot more possibilities. We're now ready to get started on our work. So let me explain to you how do you know to use this substitution method and not addition elimination. Well, first off, notice that the second equation has x squared, then y squared, then equals, then 25. To get addition elimination to work, this would have to have the same format, an x squared, then a y squared, then an equals, then a number. It's got the equals in the number, but it doesn't have x squared and y squared, so there's no way we can add to eliminate. That means we have to do substitution. To do substitution, we look for a variable with a 1 coefficient and a 1 power. That means that either the x or the y out of the linear equation are good choices. So totally up to you. You could either write x equals 5 minus y, or you could do y equals 5 minus x. Whichever one you want to use, let's take that and substitute it into equation 2. Be sure that you use both equations. If you only use one equation, you're going to get a dependent system because you've only used one equation. So let's take this one. We'll solve for x, and let's substitute for x in equation 2. So this is going to give me an equation 2. Replace the x, and notice the square stays outside. So in here is where I'm going to be dropping that 5 minus y, and the rest of equation 2 is plus y squared equals 25. So in here I drop 5 minus y, and then I'm going to have to simplify it. In order to simplify this, I need to multiply out this binomial that's being squared. Now I find it easier to go ahead and write it twice. That helps protect me from making careless mistakes. So when I do the distributive property, or FOIL as we say in the US, I get 5 times 5, which is 25. The outside gives me a negative 5y, the inside gives me a negative 5y, and the last term gives me a y squared. Then I have this part, which was already there. So this part is going to come down to this part. Okay? So I still have another plus y squared equals 25. This gives me 2y squared, and I'm going to list it first so I can get it in descending order. Negative 5y minus 5y is a negative 10y. And then I have plus 25, I'm just cleaning up the left, equals 25. Now I've got to get everything on one side and 0 on the other so I can solve. So I move the 25 from the right to the left by subtracting. That actually cancels that term, and I get 2y squared minus 10y equals 0. Now I can factor out a 2y. I could also divide both sides by 2 to get rid of it. And this gives me y minus 5 inside parentheses. This means that either 2y equals 0, in which case y has to be 0, or y minus 5 equals 0, in which case y equals 5. Now this is two different ordered pairs. This is not the same ordered pair. These are both y coordinates. So I'm going to take each one in turn and substitute back into my substitution factor, which was x equals 5 minus y. So now what I'm going to have is I'm going to have x equals 5 minus 0, which would still be 5. So this ordered pair is 5, 0. So has to cross at 5, 0. Now for the other one, I'm going to have x equals 5 minus the other y value was 5, and this gives me x equals 0, so I have 0, 5. I have two solutions here, 5, 0, and 0, 5. I went ahead and graphed these for you so you can see what's going on. We have x squared plus y squared equal 25, which is the equation of the circle of radius 5 centered at the origin, and x plus y equal 5, which is the line y equal negative x plus 5, crossing the y-axis at 5 with slope negative 1. And you can see that they do cross at those 2 points. Let's now take a look at the next one. I would like you to pause the video, work out the solutions, then turn the video back on to compare your answer to mine. So let's take a look and see how you did. In this problem, it's already set up to substitute for y. Y has a positive 1 coefficient, and it's already solved. Y equals x minus 6. X is not a bad choice either, but you'd have to move the 6 to get x equals y plus 6. Both will work. I substituted using equation 1, and I substituted for y in equation 2. This substituted in x minus 6 in place of the y in y squared. Then I multiplied it out and combined like terms. Then I moved the 26 to the left so I could get 0 on the right. Then I noticed that every term was divisible by 2, so I divided every term by 2, which gave me this quadratic equation. I factored the quadratic equation, set each factor equal to 0, and that gave me 2 possible x coordinates, 5 and 1. Then I came back up here and used the equation where I'd solved for y equals x minus 6, and I took each x coordinate in turn and substituted it in for x. That gave me 2 ordered pairs, which you see here. Now, when we're looking at this, x squared plus y squared equal to a constant is a circle. The radius of this circle will be the square root of 26. Y equal x minus 6 is a line, slope 1, crossing the y-axis at -6. Let's now look at the graph so we can verify that our solutions are the 2 places where the line crosses the circle. Now we're going to take a look at problem number 3, which is very similar to what we've done before. Y equal x is the identity function, slope 1 crossing at the origin. X squared plus y squared equals 16 is a circle of radius 4. So either it never crosses, or it touches once, or it crosses twice. These are our possibilities. Pause the video, work out the solutions, then turn the video back on. In this particular problem, because we have the identity function, it's simple to substitute for either one. You could substitute and say x is equal to y and substitute for x, or you could say y is equal to x and substitute for y. I chose to substitute for y. The equation that I substituted came from 1, so it has to go into 2. Write equation 2, leaving an empty set of parentheses in place of the variable y, and then substitute what you have for y into it. This gives me x squared plus x squared is 16, so 2x squared is 16. I divided both sides by 16 to get x squared equals 8. Then I can take the square root of both sides. The side without the variable gets a plus or minus, and the square root of 8 is 2 square roots of 2. 2 square roots of 2 is about 2.828. Now, because y is equal to x and x is equal to y, that means that the coefficients in each ordered pair are identical. They're both 2 square roots of 2, or they're both -2 square roots of 2. When we look at the graph, we can see that, in fact, that is exactly what Desmos found. It's crossing in quadrant 1, where they're both positive, and quadrant 3, where they're both negative. Now let's look at problem number 4. This is going to be similar to what we've done before. This is not the identity function because the slope is -1. In this case, it'd be easier to substitute for y, since y is already solved for x. And we have the circle x squared plus y squared equal 4, which is a circle of radius 2 centered at the origin. Pause the video, work it out, then turn it back on to compare your answer. I again substituted for y since it was already solved for y, that's less work. And I substituted it into equation 2. So -x got replaced, or y got replaced by -x. Now notice that the -x is inside the parentheses. This is why the parentheses are so important. This is going to square both the negative and the x, which is going to give me a positive x squared. That gives me 2x squared equal 4, or dividing by 2, x squared equals 2. So I get x is plus or minus the square root of 2, which is about 1.414. This time, though, the y and the x have an opposite sign. So if x is positive square root of 2, y is negative square root of 2. This is going to be in quadrant 4. If x is negative square root of 2, then y is positive square root of 2, which places this in quadrant 2. Let's look at this intersection points on the graph. And you can see that that is exactly what we found. Let's move on now to problem number 5. Problem number 5 is a little bit different. This is actually a vertical line, x equal to -1, and this is again a circle of radius square root of 5 centered at the origin. It will work the same, but here we have only one possible thing that we can solve for, and that's x. It's already solved for x. Go ahead and pause the video, work it out, then turn it back on. So this time we have a circle interacting with a vertical line. So again, we still have 3 possibilities. It could just barely graze it on one side, or it could not touch it at all, or it can cut through at 2 different points. This time when we substitute, we are going to have to use the substitution x equal -1 to substitute for x in equation 2. Rewriting, this gives me empty parentheses squared, and I replace them with -1. -1 squared gives me +1, so I have 1 plus y squared equals 5. Then I move the 1 to the opposite side to isolate the y squared. Y squared equals 4, taking the square root of both sides. The side without the variable gets a plus or minus, and I get y equals plus or minus 2. Now, x is always -1. Equation 1 tells us that. So both x coordinates are -1, but the y coordinates change from 2 to -2. Looking at the picture, you can see that that's exactly what happened. We have the circle and it cut through at 2 places, and we have the 2 solutions. Here's problem number 6. Problem number 6 is slightly different in that this must be a parabola because we have x being squared, but not y. So equation 1 is a parabola, and equation 2 must be a line because we have x to the first and y to the first, and they're subtracted together. So I have the intersection of a parabola and a line. So again, possibly no solutions. I could have 1 solution, or I can have 2 solutions. So let's now solve this problem. Now, you have a choice here. You can do it a couple of different ways. It is actually possible to do the addition elimination method here. The problem is the x squared and the x don't match. They're not alike. So it will give you a quadratic in x if you add these together to eliminate the y. It is much safer to go ahead and solve for either the x or the y from the linear equation and substitute it into the parabola. If you use the addition elimination method, you may introduce false solutions. You would need to check to verify it's on both equations. Let's go ahead and solve this one together. So I'm going to number these as 1 and 2. I need to take my substitution expression from equation 2, which is the line. The x has a 4 attached, which means I'd have to divide by 4 to isolate x. But y, even though it has a negative attached, also has the coefficient of 1. So I'm going to go for y. So I'm going to rewrite this as 4x plus 49 equals y. Or if it bothers you to have the y on the right, just switch it around and move it to the left. All I did was I added y to both sides of this equation and added the 49 to move it to the left. Okay? And this gives me a new equation 2, which I'll call 2b. And I'm going to take 2b and I'm going to substitute for y in equation 1. In equation 1, I have -4x squared plus y, so I open up an empty set of parentheses, then equals 1. I'm going to be substituting this 4x plus 9, which is going to go in this space here, which represents the y value. So now I have 4x plus 49 dropping into the hole. And then I can go ahead and simplify. I can drop the parentheses because the coefficient is +1. So I get -4x squared plus 4x plus 49 equals 1. The next thing I'm going to do is subtract the 1 to get everything on one side of the equation. This gives me negative 4x squared plus 4x plus 48 equals 0. Now, I don't like the x squared term being negative, so I want it to become positive. But notice that all the coefficients are multiples of 4. So I'm going to divide not by 4, but by negative 4 to reverse all of my signs. So this is then going to give me, and I'm trying not to do too much in one step. So then I'm going to divide each term by negative 4. And obviously, if I were solving this for myself, I would use fewer steps, but I don't want to lose anyone, so I'm writing it out longhand. This gives me x squared minus x minus 12 equals 0. Now I'm going to take that quadratic equation, x squared minus x minus 12 equals 0, and I'm going to factor it. The two factors of 12 that subtract to give me 1 are 3 and 4. So I need a minus 4 and a plus 3. And this will give me two possible x values of 4 and negative 3. Then I can take the expression I have up here where I solve for y to find the y values. So now I have y equals 4 times 4 plus 49. And this gives me 16 plus 49, which would give me 65. All right, so keep me honest here. I think I've got 65. Now let's plug it into the other value for x. So we have y equals 4 times negative 3 plus 49, which gives me a negative 12 plus 49, which I believe will give me 37. So I have two ordered pairs, and I'm running out of room to write them. Let me see if I can scroll down a little bit. My two ordered pairs that I got for solutions are 465, which is way up there, not likely to have found it by myself, and negative 337. Oh, wow. Okay, yeah, not likely to have found these on my own. Algebra helps us by finding the exact values. And when we're looking at this one, you can see on the graph that we do have the interaction of a parabola here in blue and a line here in red, and we did find the two correct values for the intersection points. Now I'm going to let you go ahead and solve this one on your own, then turn the video back on to see what we get. I followed the same process in this problem. Again, as long as you take the linear part and solve for either x or y, you won't have to worry about extraneous solutions. The negative 4 attached to x makes it a bad choice, but the y is a positive 1y, so I added 4x to both sides to isolate y out of equation 2. Then I'm going to take this expression for y and substitute for y in equation 1. Writing equation 1 with an empty set of parentheses and substituting, and then simplifying leads to this equation here. Every term is divisible by 4, which leads to the trinomial x squared plus x minus 6 equal to 0. Factoring gives us x plus 3, x minus 2, which gives us solutions of x equal negative 3 or x equal 2. Then I come back up here to where I had solved for y, and I use that with the found x coordinates to find the y coordinate associated with that x. That gave me two ordered pairs, which you see here. Looking at this equation here, I can guess that this is a positively sloped line, but it's crossing the y-axis way down there at negative 26. If you look at it in this form, it's more obvious. I've got 4x squared plus y. If I solve for y, I'd have a negative 4x squared, which must mean it's been reflected down, and it's also been shifted down by 2. So if I look at it, you can see the two curves interacting here. The line here is in red, and that's going to give you 2 points of intersection with the downward opening parabola here in blue. I want you to go ahead and solve this one. This one is a little bit more difficult because our line has a coefficient on both the x and the y. However, in this case, we can divide both sides by 2, and then we'll have it solved for y. So pause the video, work it out, then turn it back on. Now take a look at what I've done here. I took the line again to solve for one of the variables in terms of the other, and I got y equals 24x. Since this came from equation 2, it has to be substituted into equation 1 in place of y. Then I simplified the equation, moved everything to the left, and divided by a common factor of -4 so I could have a positive leading coefficient. This led to the trinomial x squared minus 6x plus 8, which is equal to 0. So I factor it and I solve for the 2 solutions, x equal 2 and x equal 4. Then I use the expression for y, which was 24x out of equation 2, to find the y coordinate that matches each individual x coordinate. This one is actually quite difficult to find on a graph. And the reason is it goes up really high, and these are very, very close together. I had to play with the scale of this in order to get it far enough apart and all on the same screen at the same time. Notice that I'm basically going from about -8 to 8, but my y value is going from 0 to 120. I had to make it really tall in order to find them both. It can take a lot of time if you're trying to solve it graphically. Now what we want to do is turn our attention to the last problem in the section, which is problem number 9. In problem number 9, we have a little bit of a different type situation because we have x squared plus y squared equal 32, which is a circle of radius square root of 32 centered at the origin. Now, y squared equal x squared, this is not one we're used to seeing. Now, you know if you were to solve for one or the other, you'd get y equals plus or minus the square root of x squared. And the square root of x squared would be the absolute value of x, so we get plus or minus x, which means that either they have the same sign or they have opposite signs, which gives us the line y equal x and the line y equal -x when we graph it. So this time I'm going to go ahead and show you the 2 graphs that we have right here. So how did I know what y squared equal x squared looks like? Well, if I take the y squared equal to x squared and I solve this for y, I take the square root of both sides, which means on the side without the y, I have to have a plus or minus, and then I have the square root of x squared. The square root of x squared is the absolute value of x. And then this gives me y equals plus or minus the absolute value of x. So it's either the positive absolute value of x or the negative absolute value of x. The positive absolute value of x, of course, is this one right here that you see opening up. That would be y equals the positive absolute value of x. Y equal the negative absolute value of x, you're going to see on the bottom. That would be this one here, which is this part right here. And then you can see we have our circle of radius square root of 32, which is, of course, 16 times 2. So 4 square root to 2, whatever that turns out to be, a little bit more than 5. So now we want to go ahead and solve this algebraically. So we're going to do this one this time by substitution, and I'll also show you how you can do addition and elimination. Both will work in this particular case. If I do substitution, then I need to solve for one of the x squareds or y squareds. Now, the only way that this will work is if both equations have an x squared or y squared. They both have x squared and they both have y squared. And I already have out of equation 2 that y squared equals x squared. So I'm going to use equation 2, y squared equals x squared. And you can use either direction. And I'm going to substitute for y squared in equation number 1. Equation 1 has the equation x squared plus y squared. This time I'm not replacing y, I'm replacing y squared. So this replaces y squared. There's no square on the outside, and it equals 32. So I'm going to substitute the x squared on the inside. So I'm substituting this for y squared. And this leads to 2x squared equals 32. And then I can divide both sides by 2. So I get x squared equals 16. Take the square root of both sides with a positive or negative on the non-variable side. And that gives me plus or minus 4. Then I can go back up here and I can solve for y. Now at the moment I have y squared equals to x squared. So I've got x equal 4 or x equal negative 4. But my equation, my substitution was in terms of y squared. So in order to use it, I'm going to have to write y squared equals plus or minus the square root of x squared. Right? So this will give me the y value. Okay? So when I'm looking at this, y, which is the square root of y squared, will be plus or minus the square root of x squared. So when I substitute this time, I get y equals plus or minus the square root of 4 squared, which of course is going to give me 16, but it gives me both positive 16 and negative 16. So I get 2 ordered pairs, 4, 16, and 4, negative 16. And then when I substitute for negative 4, because I'm squaring it first, I actually end up with 16 again underneath the radical. It's squared before we applied the radical. So this gives me plus or minus the square root of 16, which again is plus or minus 4. So this gives me 2 more possible solutions. Oops, I put 16 here, it should be 4. I just picked up on that when it changed in the other one. So that's 4, 4, and 4. And this becomes negative 4, 4, and negative 4, negative 4. So I actually have 4 places where this double absolute value is intersecting with my circle. And when we look at it, we can see that those are, in fact, the places where they cross. Now, I want to work one more type of problem for you as a sort of a warning as to what you should probably not do. So before I want to backtrack a minute, before I get into what you should not do, I want to work the last problem using the addition elimination method. It's the only one in our problem set where that's really even a reasonable choice. When I'm looking at this system of equations again, I've got equation 1, x squared plus y squared equals 32, and equation 2, y squared equals x squared. The format for equation number 1 is x squared term, then y squared term, then equals, then constant. I want to go ahead and try to get my second equation to match that. To do that, I'm going to subtract the x squared, which will move it over here to the left and leave 0 on the right. So my equation 1 is not going to change. It's x squared plus y squared equals 32. But my equation 2 is now negative x squared plus y squared equals 0. Notice that the formats are identical again. I've got x squared over x squared, y squared over y squared, constant over constant. Notice also that the coefficients of x squared are both 1s, but with opposite signs. This means that I can add them together to eliminate the x squared term, which will give me 2y squared equals 32, which gives me y squared equals 16, which is basically going to give me that y is equal to plus or minus 4. And then I can come back to this equation up here I have x squared equal to y squared, and I can solve for the x variables. I'll get the same solutions. Now let's talk about what is a risky thing to do and might introduce some false solutions. Let's take a look again at problem number 8. So we have equation 1 and equation 2. I have been doing in every problem, if there is a line, I take one of the variables of the line to solve for y in terms of x or x in terms of y. What if you decided instead, because you had a y to the first in the parabola, equation 1, you wanted to solve for that y? So if I did that, then coming up here, I would have the negative 4x squared plus y equals 32. So to isolate the y, I would add the 4x squared to both sides of the equation. This would give me y equals 4x squared plus 32. Then I would substitute for y in equation 2. In equation 2, then I have 2 times something equal to 48x. My something is the 4x squared plus 32. Oops, erasing a little bit. So this expression here gets substituted for y in equation 2. Then I need to multiply this out, or I could divide both sides by 2. That might make it a little easier. And I get 4x squared plus 32 equals 24x. I need to move the 24x to the left, and I get 4x squared minus 24x plus 32 equals 0 in descending order. Then they're all divisible by 4, so I can divide each term by 4. And I'm going to write that as multiplying the whole thing by 1/4, which will give me x squared minus 6x plus 8 equals 0. In this case, we end up, I believe, with the same solutions that we did last time. We get an x minus 4, x minus 2, which gives us 4 and 2 as our possibilities, and then we can substitute back in to get the solution. However, it is possible when you're doing this that you end up with something that is extraneous, and that will happen if when you substitute it, you square it. If when you substitute, you square it, you always have the possibility of an extraneous solution. So be careful and watch for those. I hope you'll join me for the next video where we actually have a lot of fun exploring what matrices are, learning to add them, subtract them, multiply them by constants, and even to multiply matrices together. Then we'll use matrices in our last section to solve systems of 3 linear equations, 3 lines all at the same time in 3 variables. So that's 3 equations in 3-dimensional space, which gets pretty complicated. I'll see you for that video down the road.